Okay, welcome to the Computational Sustainability Virtual Seminar Series. This virtual seminar is being organized by CompSusNet with support from the National Science Foundation and Cornell University. We are happy to offer this opportunity for those interested in computing and sustainability across the globe. My name is Doug Fisher, and I'm the Director for Outreach, Education, Diversity, and Synthesis of CompSusNet. During the webinar, you can ask questions through chat or the question and answer facility on Zoom, and I'll be monitoring those and relaying them to the speaker as time allows. We have a fair number of talks already that we've already given, and you can find videos for those talks at the URL at the center of this screen. You can also find a schedule of future talks. In 2 weeks, we'll have Vipin Kumar from Minnesota speaking to us. But today we're thrilled to have Dr. Scott Worland. He's a hydrologist at the U.S. Geological Survey, and he's also a very recent PhD from Vanderbilt University. So it's a particular pleasure to invite him to talk today. So Scott, I would turn this over to you, and you can begin whenever ready.
All right, let me.
You are coming through fantastic.
Great. So can you see the full screen?
Ken?
Okay. All right, well, as Dr. Fisher said, I'm Scott Worland, and I actually just want to give a special thanks to Dr. Fisher. Not only did he invite me to do this talk today, but I took my first class in modern machine learning from him, and before that time I had been primarily using conceptual-based hydrologic models, and it really inspired me and became a jumping point for me to do more data-driven hydrologic modeling, and that really ended up becoming like the bulk of my dissertation as well. My other collaborators on this are Scott Steinschneider. He's a statistical hydrologist at Cornell, and then George Hornberger is a hydrologist at Vanderbilt University, and he was also my PhD advisor. So this is, the diagram that's on the CompSusNet website. Just looking at this earlier, I think I can place this talk somewhere down here on the lower left. So balancing environmental and socioeconomic needs are something that hopefully every government scientist is trying to do, but we are really approaching this from a very data-driven perspective. So I'm going to provide more background than I might normally do, primarily because I realize not everyone on the call is a hydrologist or even environmental scientist. I think it's important to understand how this research fits into the overall context of hydrology. And so I'm going to start with a pretty basic concept. And I'm part of a team, and we have this somewhat ambitious but simple goal of trying to balance water budgets at fine temporal and spatial scales. And what I mean by fine spatial scales, we're using HUC-12s, which is a code for a watershed, and it's something that you could easily walk across in a morning. They're about 25 to 40 square miles, and ultimately our goal for a time step would be daily. And so what I mean by a water budget is precipitation provides input to a watershed, and then the things that can cause water to leave a watershed is obviously discharge from a stream, evapotranspiration from plants or surface water, and then change in storage. So change in storage is groundwater either leaving or coming into a basin, and that actually could be a contributing term as well as something that's pulling water out of the basin. So for a long time, hydrologists just completely ignored biology. And it was this assumption that made the math a lot simpler for models. And in the 60s, 70s, and 80s, and up through now, hydrologists have realized how biology is probably some of the most important part of the water cycle, and we definitely incorporate it now in things like ET. But you might notice that there's still a large missing term from this water budget. And that term is human water use. And in lots of locations, particularly places like the Mississippi alluvial plain, where you have a lot of agriculture, human water use can be by far the biggest term in over long time scales can be one of the biggest terms, and for certain seasons this whole budget. And so what we're trying to do is look at the three largest sectors of human water use, thermoelectric, irrigation, and municipal supply. And we are trying to incorporate that into these small scale budgets. And so this plot here just has year on the x-axis, and the y-axis is per capita water use. And this is for the US. This is a national number. And we have, we can handle thermoelectric and irrigation pretty well already in these water budgets. For thermoelectric, we have a heat budget model that we can use, and for irrigation, remote sensing is a pretty straightforward way to get that information. Municipal supply is the third largest, and it is one that we do not have a good handle on for lots of reasons that I won't go into here. But that serves as the reason that we're trying to understand some of the explanatory variables that are associated with municipal supply, and so we can ultimately incorporate that as well into these budgets. So what I mean by municipal supply is there's some centrality that extracts water from the source. That source may be a stream or groundwater. It normally treats the water and it either stores it or it just delivers it straight to an end user. And the primary end users for municipal supply are going to be residential, commercial, and industrial. Oftentimes industrial, if it's large enough, they would rather just withdraw their own water and treat it for their own purposes because it can be a lot cheaper. So the primary end users are really residential and commercial. And our question is, well, in locations that have the same number of people, there can be great variability in how much water that they use. And so we're trying to understand that better. And so some simple things that can change how much water is withdrawn is outdoor water use is a large one, right? And this just adds back into that water budget where we have ET, you're obviously increasing ET, and if you're in places that doesn't have much rainfall, then it takes a lot of extra irrigation to keep that outdoor vegetation healthy. And so that can cause water use to go up. Things that can cause water use to go down is obviously something like precipitation, where places in the southeast, you might not have to irrigate your lawn, but a couple weeks for a couple months out of the year. We're obviously not the first ones to do some research in this area, and this site list here in the left column could, go on for pages. And so I just pulled out a few that were particularly relevant and interesting to the work that we were doing. And so, like two things I've already mentioned, as rainfall goes up, most of these studies will find that water use goes down. As lawn size goes up for outdoor water use, we just talked about that water use may go up. But what we're really interested in is some of the socioeconomic and other climate variables that aren't as obvious. One of the more obvious ones is price. Water is fairly inelastic, but still as you increase water price, water use does tend to decrease. Age of building is also shown in lots of studies to increase water use, and this is normally due to aging infrastructure or leaky pipes, things like that, and also less efficient appliances can lead to more water use. Conservation policies may seem fairly obvious, but there's been some really neat studies done lately that explore the effect of conservation policies in places like California, and you can look at the memory in the system after conservation policies are after the conservation policies are lifted. People still tend to conserve water. I see a bunch of chats going on. I'm going to click on that because I don't know if I'm supposed to or if those are questions.
I'll monitor that for you, Scott.
Okay.
If you want. People are just saying hello.
Okay, great. You just kept popping up.
And yeah, I'll make sure I monitor that. But
okay. And this paper that's highlighted in red and the remaining explanatory variables I'm going to mention is particularly relevant to our research. So we were just about to submit a version of this paper, and I was asked to review this paper here that's in the red, and it was interesting timing because it was very similar. We're using the same base data set, and we were trying to look at some, we had some very similar research questions. And so I reviewed the paper, waited till it was published, and then we kind of took a fresh approach. We were using very different modeling approach already, but we sort of took a fresh approach to our research questions and really used their paper as a starting place. So some of the things that they found was that more rural areas tend to use more water. higher educated places tend to use less water, and that was the same for income. And I'll come back to those at the end of the talk, how our findings relate to that. So that's basically the hydrologic context, but I think it's just as important to explain how we're thinking of this problem statistically, because I think it'll help understand why we chose the models that we have, and how we're sort of interpreting these results. And so hierarchical models have a bunch of different names, and I'll try to be consistent and refer to them as either hierarchical or partially pooled models. I particularly like partially pooled because it gives some idea of how these models actually work and what makes them so effective. And this is because the basic question, if you choose to do a hierarchical model, is, are there groups in the data that might be important? And so on the left, you'll see an example of a fully pooled model. And that argument would be, you take all the data you have and you just throw that into one model. You don't think that there's interesting variation in it, or if it is interesting, you don't think you can really account for it. An unpooled model would be, you think the groups are so distinct that they need their own separate models. And partially pooled is a blend of these, where you recognize that there are groups in your data that are relevant, and you want to account for that, but you also know that that shared information is really important. And what's really neat about these is simultaneous to group level parameters, you also have these higher level parameters that are estimated, which constrain the values of the group level parameters. And you can see in the equation on the bottom, this is just a simplified version of Bayes' theorem, where we don't have the normalizing constant denominator. We have a posterior on the left, and what we want that's what we want to estimate, and we do that with a likelihood times a prior. And you could think of theta and omega here as being two different levels of parameters. So theta would be this group level parameter, and omega would be this higher level parameter. And you can see that omega only comes in the partially pooled. So for the fully pooled model, you would just be estimating one parameter for all of them. For unpooled, there would be these three separate ones. And for partially pooled, you would have three separate parameters for each group, but they would be controlled by omega. And you can see how, if you look at the second line of the equation, how it's factors. So any model that can be factored into a chain of dependencies like this is a hierarchical model. And so rather than, at this point, belabor any more of the mathematical background, what I'm going to do is use a simplified example using some of our data, which I think should make it very clear how we're thinking of this and how we're using these models in this way. This plot is the gallons sold per account for cities in the US. And the basic research question might be something like, okay, well, what explains this variability? And there's, the basic way that you might do this is you would just go to the literature, find some explanatory variables, and build a big model. But the other question, kind of going back to this hierarchical idea, is, well, are there groups in the data that we would like to capture information from? And so this is 9 different climate regions that are provided by NOAA, and you can see how there's, these cities kind of group into different regions across the US. And conceptually, the question is, well, do you think that the response of water use in these cities is the same for the south, relative to some explanatory variable, is the same in the Southeast as it is in the West? And so taking a simple socioeconomic indicator, the regional price parity, which is on the x-axis in this plot, which this just tells you how expensive a city is to live in relative to the national average. So here it's how much does $100 cost. So if it's more than 100, it's expensive. If it's less than 100, it's a little bit cheaper area to live in. And the y-axis is just gallons per account. So there's 2 things I hope you can take away from this plot, right? You have, without even building a model, you know where the maximum likelihood least squares estimate is going to be, right? It's going to give you somewhat of a positive slope, but you also see there's a lot of uncertainty in that. And I think those are 2 things that we would like to capture in a good model. And so this is even, you can see that the certainty is even further increased when we look at this for all these different climate regions. So, for example, if you look at the Northeast in the far top right, you can see that, yes, there maybe is still this positive trend. But for other locations, there's either no relationship or it could even potentially be negative. And so if you look at the west, north, central in the bottom right corner, that's two cities. You can't see it very well in this plot. But there are two cities in the west, north, central region, Sioux Falls and Lincoln. And those have almost the exact same values on both axes, so how are you going to build a model that accounts for something like that? So the first thing I'm going to show you is if we just took all of the data, right? So we just build a model using regional price parity and gallons per account. And I'm going to draw 50 draws from the posterior distribution of alpha and beta. And I'm going to plot those lines and show you what that looks like. And this is what I would call, the most basic naive approach to this. And so these lines, although there are different lines, notice that the panels all share the same lines, right? Because this is a model built using all of the data. I just superimpose the lines on all the different regions so you can see what the model is suggesting for these different regions. And in some places it's okay, in other places, it tells you there's this relationship that you definitely don't see in the data at all. And I think worse than that is it's very certain about that relationship, right? Because you're using all of this data, reduces the uncertainty, and it makes you overconfident in your parameter estimates. So another option is, well, why don't we just build a model for each climate region independently? And I'm going to show you what that would look like. And hopefully the first thing that jumps out to you is, well, at least it's a lot more uncertain, but in most places it's so uncertain that the model is basically useless. So for example, again, in the west, north, central region, in the right bottom plot, keep in mind there's two cities and there's two parameters, so there's literally an infinite number of possibilities, a combination of those parameters that you can use to estimate a model for that region. And so, like I said earlier, what we would like to do is take the overall trend from this pooled estimate and the uncertainty in this unpooled estimate and estimate a partially pooled model. And this is the results from that. And what you can see is it does just that. For locations that don't have very much data, it still says, okay, well, we don't know very much about this region, so let's just basically say that it has something similar to the overall trend of this slightly positive relationship. But you can also see that there's a lot of uncertainty associated with that, which is really desirable when working with these messy types of data sets. And you can also see that the confidence, which is indicated by basically how dark these lines are, the confidence in the parameters is directly proportional to how many data points there are in each region. So again, this is just a setup. This is not necessarily a model that we present in the paper or anything, but this is just to give you some idea, of how we're thinking about this before we move on to something a bit more complicated. So this is the same response variable, gallons per account, but now we're going to add in some other explanatory variables. Water price, bill type tells you whether it's an increasing, decreasing, or flat block rate. The number of rebate conservation policies, the number of requirement conservation policies, an aridity index, which it's slightly confusing here. Positive aridity means, a positive value of the aridity index means more humid, and a negative value means more arid. It's just how the index calculates the numbers. And then regional price parity, again, the one that we just discussed. And because these, all of the explanatory variables were scaled prior to the analysis, I'll also show you the standard deviation, right? Because that becomes the new unit change that we're interested in. And I'll come back to that in just a moment. And then this is a fairly simple model, so I'm just going to show it to you again for a fully pooled estimate. And basically, you can see that there's the different coefficients in front of the explanatory variables, and they're all given their own unique prior. And that's indicated by beta 1 through 6. They're all given separate priors. I'm going to show you the results for that, and then to explain a little bit about how it relates to these different variables. So this is the full posterior distribution for each of these parameters. And regional price parity is on top, and it's like we saw from the data. Even after you control for all of these other variables, it still says that it's positive and it's fairly significant. And really what I mean by significant is, there are obviously tests that you can use, but does it overlap zero? That's really the thing we're interested in these posterior parameter estimates. And then things like requirement and bill type, rebate, they definitely have a lot of the distribution overlap zero. So we don't think there's much information there. But then aridity and water bill are both negative, which is what you would expect. So as aridity, in this case, decreases, so as humidity increases, you get less water use. And then water bill, as you increase water bill, you're getting less water use as well. And so what this means, break it down into really simple terms. You can take the mean, let's say, if that water bill estimate is somewhere around maybe negative 30,000, something like that. And so knowing the standard deviations, $11.50, it's saying, based on this model, if you increase the water bill by $11.50, you're saving around 30,000 gallons per person or per account. So rather than show these full posterior distributions, because this can get really messy quickly, I'm going to show summaries that look like this. So note that these two plots are showing the same information, but here I'm just taking the mean of the distribution and assigning a white triangle. And then the 50th percentile is the thick lines, and the 80th percentile is the thin black lines. But also, I think it's actually really nice to be able to see the full posterior first and see things like, if you look at aridity, some of the distribution does overlap zero. So when you're trying to interpret significance, but when you summarize it like this, it doesn't, and I think you just have to keep in mind that the tails of the distribution are being lopped off when you do it this way. And so you have to take some of these parameter estimates with a bit of caution. So that was the fully pooled model, which is not necessarily what we're interested in. And what we really want to know is, well, what if we account for climate regions? And so this is similar to earlier, how I was explaining, these models that these partially pooled models, they share information up to these higher level parameters. And all of this plot on the right is relevant to how we actually set up the models. But I think the most important pieces are what's here in red. So there's a linear model that's associated with the data. And those parameters that are estimated from that linear model are given a multivariate normal distribution. Right? And this multivariate normal distribution has a covariance matrix, which is also estimated from the data. And that covariance matrix is what tells you, how are these different regions related, and it accounts for the different sample sizes in the regions. It tells you how are they related, but then also what it does allow is, because you're drawing from this multivariate normal distribution, it does allow varying parameters for the different regions. So this is the same plot as I showed earlier. The only thing to note is if you see the star, let me come back here. So the star is the diamond from this plot right here. So I just pulled that off and plotted it. So it's the same for each parameter in each region. It's the same value. I'm sorry, it's the same value for each region. Obviously, it varies by parameter. And the reason I did that is so you can see, well, how far does each climate region, how far does it vary from the fully pooled estimate? And, without making someone look at this plot for too long, there's a few quick summary points. One being, I don't think there's enough information in this data to say very much about these regions, which that probably seems like somewhat of a boring result, but I think that's where things are actually relevant, because if you ask somebody, what do they think controls water use? A lot of people would list these things that we have here as explanatory variables, and at least in these regions, it seems to be, there's either not enough data to really say very much about those variables. And what remains is water price and regional price parity. Regional price parity is positive for most of the ones that is significant, and water price is negative, which is what we saw with the fully pooled model. But one thing you might notice is that aridity is no longer significant. And that can be explained because the climate regions are accounting for the first order effect of climate you can think of on water use. And so once you account for that, the question then becomes, okay, once we know all of these regions are somewhat similar in terms of climate, does inter-region climate variability have much effect? And at least with this data set, we don't see that that's the case. Then this is the observed versus predicted for these two models. And again, we're not actually at this point building a predictive model, or not, of course predictions are made, but what we're really interested in is the size and the effect of the explanatory variables. But I think it is worthwhile to note that when you do partially pool these models, it doubles the R squared. And this is, obviously fairly common because you're adding information that wasn't available in the fully pooled model. What it also tends to give you is much better out-of-sample predictions. But again, if we were going to build a predictive model, I don't think this would necessarily be the approach that I would take. Although obviously it could serve as that. But I did want to show that it does do a decent job of predicting, but it does not do a very good job for the cities that are very high water use. It tends to always underpredict those, which is basically because there's just not enough data at those higher values. There's not enough data points at those higher values that the model can learn that relationship very well. And it's a linear model, so if you went to a more nonlinear model, the chances that you could learn those at the higher observed values is better. So I've actually given this talk backwards from the paper, and I did that because the paper starts with what I would say more complicated models and gets somewhat simpler. But the motivation for doing it that way in the paper was we originally set out with this county level data, which has a lot more data, but there were certain explanatory variables that we were interested in, things like water price or conservation policies that we could not find for every county. And so I'm going to talk now about a little bit about the county level models and how those relate to the city level models. So this is freshwater withdrawal per household per year. And the black counties you can see are counties that we had to drop, mainly because we're suspicious that they had inter-county transfers, which is where a county is either buying or selling water across its county boundary. And that can be problematic for lots of reasons. But for one, it really confuses the design matrix for your statistics because it doesn't know there'll be a value associated with the explanatory variable that's actually from an adjacent county rather than the county where the water is actually coming from. So we just used some constraints based off the literature to cull counties that we thought were likely had these inter-county transfers, and these are the ones that remain. We also have a lot more explanatory variables. And I won't go into each one, but one thing, just the colors from yellow to purple are basically from west to east. It's not a perfect relationship, but it's close. And you can look at something like precipitation, the 40-year precipitation, which is in the middle row towards the right. And obviously, as you move from left to right, you're getting more precipitation. And some of the other ones that are more interesting is we have on the top row, the second one from the left, is the County Cook's Partisan Voting Index, which the way that we calculated is a more positive value means that more people in the county have voted for Democrats in presidential elections, and more negative means more Republican. And one reason that we chose that was just it's really a common indicator of things that are a lot more complicated to explain than simply how people vote in presidential elections. For one, it's been shown that conservation policies tend to increase a lot with the PVI, that partisan voting index. And so this idea that this county has a culture, let's say, that is a bit more self-regulating and more okay with having policies. And so you tend to see these associations. And that's actually been shown to be important in lots of different studies. And then I'll explain some of these more in a moment when I summarize some of the results. And obviously at any time, please, just stop me and I can explain more of these. But the last one I do want to make sure I touch on is the bottom row, second from the left, proportion surface water. So that is, literally just how much of the county draws water from surface or groundwater. And you can see that it's really bimodal, right? So most counties either do one or the other. So other than just explanatory variables, there are also these other grouping variables that are available to us at the county level. And so this was the climate regions that you've already seen the results for. But we can also look at something like the rural to urban index or classification. And so this is obviously just indicates how rural, so a really metro county here is yellow and a really rural county is the dark blue. And you can think of different reasons why that might drive water use, but also we were interested in this because, like I mentioned at the beginning, the paper that was written at a similar time to ours found that this gradient was very important. Also, looking at the primary economic dependence of each county, and again, you can conceptually think of reasons why this might have some effect on how much water use these locations are using. And this is, the resulting table from all of these models. And basically, just the rows just tell you a little bit about the individual models that we built. And then the most important column is this change in the WAIC, which gives you an estimate of an out-of-sample performance of the model. And these numbers are only relative to each other. So, right, we're not, the WAIC by itself doesn't mean anything, but when you compare multiple models, it does mean something. And so you can see that it goes from worst performing at the top to best performing at the bottom. And so just to give you an example, the fully pooled model, where if we just use all of those explanatory variables and all of that data in one model, you can see where it falls somewhere in the middle. But then the best model is this climate region model, like I was showing you earlier for the cities. It's also the best regions for the county. And that's the reason that we did it the way in the paper is because we'd actually calculated this first, realized it was the best model, and then we used it for the city level data. And again, it may not necessarily seem that interesting, but it is kind of, at least interesting to us as we're trying to understand this better, that, this model does do so much better than the other ones, particularly when you're looking at things like urban gradient and the economic dependency. Neither of those are really even very close to the top performing model. So it does seem like climate region is a really important, first order approximation to group this data this way. And again, this is arbitrary, right? You can think of off the top of your head 10 to 15 to 100 different ways you could group this data that would be interesting. I mean, you could bin some continuous explanatory variables. You could look at things like what type of water bill do they have. There's lots of different ways to do it. And so this is obviously not an exhaustive list, but at least among these different ones that we chose, climate region is shown to be the most important. And rather than try to step you through this, because this is obviously hard to see, basically just note where these dotted lines are. And what I'm going to do is I'm going to take those variables and I'm going to summarize it in a different way that's a bit easier to do in a talk like this. So the variables, proportion surface water is the one I described earlier, people per household, the median age of the structures in the county, and then that's the Cook partisan voting index, the 40-year mean maximum temperature, and then the 40-year mean precipitation. And these are not necessarily the most important across for every region, but they did seem to be, when you look at on average, the most important variables that jumped out. So for the central region, for example, these arrows just show you the magnitude and the direction of the effect. So yeah, for the central region, people per household tend to be the most important variable. For East North Central, the climate variables tend to be the most important, but none of the effects were really large. In the Northeast, proportion surface water, this is one of the only places that jumps out to be this large. It was very important. It was the most important explanatory variable. And places that tend to use more surface water tend to use a lot more water. And you see here for the Cook PVI for the Northeast, it has arrows going up and down. That's when the posterior distribution of the parameter estimate overlapped 0 and the mean was almost right on 0. And so we really don't know the effect of that variable. For the Northwest, you can see that the Cook PVI was the most important. So as that value increases, the amount of water use decreases. And in the South, people per household, it was really similar to the central region. In the Southeast, you have a few things. People per household and the maximum temperature, but the variables weren't very strong in the Southeast. And that's where our model actually did the worst in terms of predictive performance. In the Southwest, you can see that precipitation drives, far more than any other variable. And it's one of the largest variables that we estimated, or one of the largest effects that were estimated across all the models. And I'll come back to that in a moment. And then in the West, similar to the Northwest, the PVI was the most important, the partisan voting index. And then in West North Central, precipitation again was really important. And so going back to earlier, when I was saying that aridity was no longer important for those different city level regions, when you look at county level, precipitation still has a really strong effect in a lot of these regions, which is interesting because what that has to mean is that even after you do know that, okay, all these counties are in the Southwest, the change in variability, the variability in precip there really still has a really important effect that can greatly, I'm assuming, drive the need for outdoor use. But then if you notice in the Western region, it doesn't have much of an effect at all. So it is, you have the Yeah, the Southwest and the West North Central it does, but the West it does not. And so some of the conclusions, I think I went a little faster than I thought to, but we'll have more time for questions. So, I mean, basically, like I said earlier, this may seem like somewhat of a boring finding, but water use context really does have a strong effect over how these, for one, how much water use is used in that county or city, but then also, it modulates the associated explanatory variables. Yet there is this nationally consistent traits, right? And this goes back to this idea of if you ignore the fact that all of this comes from this common distribution, all of these parameters, you actually lose a lot of really relevant information, which is shown both by the performance of all the models and then also just by that observer's predicted plot that I showed earlier. And I already talked about this, but slight variations in rainfall, this should be northwest, not west, in the northwest climate region can greatly affect water use. And then to go back to these that the previous research found important, we really didn't see much for income and education. And I think this can be explained possibly by a masking effect. So it's it's a common thought that as education increases, environmental awareness increases, which can lead to things like water conservation. But education and income are also positively correlated, and higher disposable income means you've got more money to do things like irrigate a lawn. And so basically for us in the variables that we were using, it came out to be a wash. It was really hard to say the effect of either income or education. We also did not see this strong rural to urban effect. Which again, it could be we were obviously handling this index slightly differently. The previous paper was binning it in a certain way, and we were using it more as a grouping variable or as a continuous variable in the other models. But we didn't really see that as being a strong effect. Right, so to go all the way back to the very beginning of the talk, what does any of this really have to do with water budgets? And if you read the paper, we definitely thought the most interesting story was more of this drivers of municipal supply. But it really all goes back to this idea of how can we incorporate this information into a water budget. And so some of the stuff that I'm working on right now and we'll be working on for the next few years is we're taking county level data for water use. So this is just an example in the ACF basin, which is on the border of Alabama and Georgia. And here's some different county level water use data for different sectors. And we're trying to just aggregate that into these HUC-12s. And then the idea is we have all these other components of a water budget. Let's see how this can decrease the residuals from that more simplified model once we add water use to it. This paper is published in Water Resources Research. And then also the data and all of the scripts that I used to build the models is available on Sciencebase, which is a government hosted repository. And you can just follow this DOI and go there and download, all of the scripts, but also the data for the two separate models, or the different models. And then funding this work was funded in part by the U.S. Geological Survey, and then also a National Science Foundation grant from Vanderbilt. And with that, Doug, I finished a little early, but
it's all right.
All right.
Thanks, Scott. So I had a question. It wasn't clear to me that, actually, I might postpone mine. There is a question online from Randolph. Watersheds are traditionally defined by surface topography. How does transport by aquifers fit into the picture?
Yeah, that is an excellent question. And it's not something that we've settled yet. So one thing that it's sort of a conceptual model that you either hate or you can deal with, because there's really no great way to do this. But we're sort of considering a watershed as a 3D unit, right? So basically, if you have a map view of a watershed and you're looking straight down, the idea being that if you integrate over all that distance, change in storage does in some way needs to be accounted for in terms of an overall water budget. But it is a little weird, and it's definitely conversations that we've had about, shouldn't, particularly like a deep aquifer, does that really have anything at all to do with, watershed processes? And the answer is no. we do want to account for that change in water. And you can think of things like gray satellites, as they fly over. These are obviously pretty coarse resolutions, but they give us a change in gravity, which give us some idea of a change in storage. Exactly what depth that is, it's hard to know. We're trying to account for changes like that. But yeah, I can't say that anybody feels really settled yet about the best way to handle that. And we've talked about, maybe just talking about recharge and letting that be a term where it leaves the watershed and not accounting for change in storage. But I'll definitely be open to more conversation about that if you wanted to follow up.
Great. So you are, we had a major hydrologist speak a couple weeks ago, although the talk wasn't on hydrology per se. So if I'm not mistaken, you're probably the first water-focused speaker in the series. And it's good. I think it's an important topic, so we want to see more of it. Did I understand so you presented us first with a hierarchical model or unpooled model of by climate region in the United States. And then the second part of your talk, I think you pushed it down to county level statistics. Do I understand correctly that we could think of this as a unified hierarchical model that in which you had this first order decomposition by region and then a further decomposition of those various subtrees by county?
Yeah, so I didn't explain that very well. So not exactly. So the models are actually somewhat similar. I think I'll need to show real quick. So the first model was based off this data, okay? So this is city level data, and we're still using the same grouping variable. And then the next model that I go into is we're adding in the counties rather than cities. And like I said in the paper, it's actually reversed. So the county level data was what we were originally interested in. And as we built those models, and we had all those 18 explanatory variables, we were really remiss that we could not include water price or conservation policies. And so then we, on top of that, built the city level model using just, we only use 6 explanatory variables that are shown here. And we did that. The reason I presented it this way, because this is obviously a much simpler setup, but the setups are, it's a simpler data set, but the setups are exactly the same. Here we're using cities, hierarchical, they're partially pooled by climate regions. The next one is county level data. Jump to that, county level data, which is also partially pooled by climate regions.
Okay.
But the way you said it though is actually fine, because you are doing that in a way. You are letting these counties and these individual regions drive parameters, but they're also sharing information, between themselves, the different regions.
Right. Other questions? So my early work in machine learning was in hierarchical clustering, and I'm a great believer in hierarchical models. If you can model it hierarchically, don't, for goodness sake, model it as a flat set of clusters. But could you imagine applying clustering like this where areas, for example, counties, are not grouped by simply geographical location, but by other climate factors that they share? And you might actually group something in Arizona with something in, East Texas.
Yeah, absolutely. And so some things that I've tried, I didn't show here, like a really simple approach. I just took all the climate data and just did k-means clustering and just said, okay, here's 5 K clusters. Let's just put a hierarchical model where I don't have a great understanding of, they do tend to fall, obviously, if you're using climate data. The K clusters do sort of look like, climate regions, but, or do the same thing with socioeconomic data, which is even more interesting, right? You're grouping these counties by some sort of a k-means clustering based off their socioeconomic data and, build a hierarchical model. The problem was it was just hard to interpret exactly what it meant. But although we know it means something and it was relevant, we ended up not including it in the paper.
Okay.
But, yeah.
All right, very good. Other questions?
Yeah, actually, that was a great talk. I have a question that, can you give me the sense of the size of the data sets you are using?
Sure. So the county level data, it's close to 3,000 observations. And then the explanatory variables, we had 18.
Mm-hmm.
And then for city level, I can't remember the exact number, it was 100 something. And then we had 6 explanatory variables.
Okay. Very good. Any other questions? Okay, Scott. Well, thanks again. And hopefully you'll be joining us regularly in subsequent talks.
Okay. Well, thank you so much.